Okay, hello everybody. Good morning, good afternoon, depending on where you are. I'm Sean Richardson with Vibrant Technology. We're going to go ahead and get this webinar started. Today's focus is on using ODS videos for natural frequency testing of wind turbine towers. And our host, as has been for our previous webinars with ODS videos, is Dan Ambre from Full Spectrum Diagnostics. And so we're going to let him go ahead and run with this. Couple quick notes. If you have any questions, why don't you go ahead, you can type it in. I'll monitor the questions. If it's something I can just give you a quick answer for, I'll type it back to you. If it's something that is applicable to everybody that's listening, we'll go ahead and we'll save it to the end, and either I'll answer it or Dan will answer it for everybody. So go ahead and feel free to ask your questions in there. We'll talk about pricing and promotions and some other things like that we have going on, but at this point, I'm going to turn it over to Dan. So here we go.
Yeah, hi everybody. Sorry, it's been a while since we've done a webinar, but we're out working now. I've had about 3 straight weeks of work, and a couple of the jobs involved ODS videos, and I've had some good results. And one of those was wind turbine towers. There's a field of large number of wind turbines in the Northeast that I just worked on a couple weeks ago, and put together some a webinar out of that. I've been dying to do these for a long time. I've been inside of them up in the nacelle and looked at gearbox and generator problems and alignment and things like that. But it's a whole different animal when you're trying to take vibration data on the tower itself. It's a 280-foot high tower, and it's almost impossible to get it to behave when you want it to, because of weather and the climb and the safety limitations, and just the logistics are a nightmare. I have a list here of some of the large machinery analysis issues, more specifically with wind turbines, is the overall size. The tower's not moving, the blades are moving. There's not another format that can get you the vibration analysis and pick apart things that are rotating and things that aren't, like the ODS videos. It has a low turning speed. It's the excitation method is a little unorthodox. You don't hit it with a hammer like you normally would for doing a modal test. You use the wind as a hammer. The data capture, that was a little challenging because it's not long enough. One of these things will ring once you set it into motion for about 2 minutes. And I only had about 8 seconds of data to see what that frequency was. Fortunately, that was plenty, but it had me a little concerned for a few moments. The climb, for this, we didn't have to climb. We just took different vantage points, shot some good video, and went back and analyzed it. The climb is about at least a 20-minute climb with breaks. There's about 3 spots in the tower, and you're climbing a ladder. It is not the most fun thing I've ever done. And like always, we're a slave of the weather. On this site, first thing in the morning, had pretty good winds. By the afternoon, it was just, they were gone. So we had some starts and stops we had to deal with, and took a little longer than we thought it would, but the data turned out really well. Come on. There we go. There's several failure modes that were identified by the site manager, and some of them are listed down here. They had some cracking issues. There's some kind of fiber composite material that's on the blades, and the blades aren't steel. They're fiber plastic type stuff. Inside there's balsa wood and other things that keep them light and keep the shape. So they flex quite a bit. They're pretty flexible blades. You get leading and trailing edge blade cracking. And if you look right here where my cursor is, this is a repair of a leading edge cracking problem. And they have some more out on the edges of the blades that you'll probably see in some of the other animations. There's blade pitch bearing failure. What that is each blade will pitch in and out of the wind as desired to either pick up speed or a drop speed if it's too windy. And that ring is right here. You can't see it's buried inside the nose cone there, but that ring is about, I don't know, 8 or 10 inches thick, and the diameter's just as big as the blade. It's a big piece of metal, and some of the bad behaving wind turbines out there will crack that ring. And I thought I saw something that might lead to that as a diagnostic, and we'll check that in a few minutes here. There's gearbox wear and failure and generator wear and failure. You can't get those unless you go up in the nacelle, and we weren't allowed to do that. You can't go up there while it's operating. They don't care to insure things like that. But you can do that with traditional operating deflection shape analysis. Generator to gearbox coupling and alignment. This is something that you can see from the videos, because when we do a still shot or a frequency domain animation, we lose all rotating aspects of the turbine, and we see what its flexing mode is. I'll have to show you that as well. A lot of this analysis is done in operating deflection shape time waveform. Okay, to get all the frequency content. It's such a low speed event that you can't really do it in the frequency domain. And while it's running, there's a lot of issues with the blade pass frequency that we'll get into in a minute as well. We're down to the bottom here, the tower resonance, and this is the big problem that the site was worried about. They had a balance guy come in, and he was balancing some of the turbines, and he got on one of the units, and it scared him so bad he said he wasn't going back up, and he thought the tower was going to tip over, which it didn't. And they had me in there to take a look at a series of towers, good ones and known bad ones, and see if there's anything to this tower resonance problem. And the last failure mode is anchor bolt failure. There's, I don't know, maybe 50 anchor bolts in the base of these units, and you shoot the ground and you see motion. It's not much motion, but it's, you're at the attachment point. A little hard to interpret how much is too much, but we didn't see any cracks opening up, anything like that, which was good. Okay, some wind tower vibration analysis. Like we just mentioned, large scale machinery doesn't lend itself well to the normal traditional natural frequency testing with a hammer. This application has a 280-foot tower, and everything's a problem of scale. This case, experimental modal analysis, is the proper test method. We're going to use the MEscope ODS videos to accomplish that, but basically this is MEscope EMA videos because we've proved out what we can do with natural frequency testing on large components like this. So this video analysis that we've talked about over the last few weeks and a couple months is a high-speed video vibration analysis. The video clip is processed with an optical flow algorithm, which enhances the subtle displacement and rescales the amplitudes. It allows users to see what the human eye can't see. So it both slows down the motion and increases the amplitudes of motion. Okay, so even if the event is too fast and the displacements are too small, we can accommodate for that and see the motion that is in the structure. And it actually is a fantastic format for wind turbines. That being said, we did have a few problems. The first time we tried to look at tower motion was with it operating, and we were doing a normal ODS video operational test, and the blade pass frequency was too high. Every time the blade passes the tower, you'll get a pulse, that compression of air between the tower and the blade, and you get 3 of those per revolution since there's 3 blades. Those peaks were so big that they encompassed everything. I could still put my cursor on turning speed of the shaft, but they're balanced enough that you don't even see that. So we had to figure out, well, what are we going to do next? And the way to go was the time waveform animation. So we set up a methodology. We started with an operating turbine, and we synced it to the grid. And the top picture here is the blade setting for normal operation. So you set it so that the leading edge captures that wind and turns the turbine. And once it's at high enough speed, everything lines up and it syncs to the grid, and you start generating power. Now for the natural frequency test, we don't want it to be running, we want to shut it down. And when we shut it down correctly, you take all that energy that's spring loading the tower and you're stopping that. You're commanding the blades to get pitch into the wind, and you lose that force that's causing the tower to flex in one direction, and it lets go like a cantilever beam and just sings at its natural frequencies. And you should get two. You should get one in the axial direction of the prop and one in the lateral direction. And we were seeing both of those. And there's some guidelines for what they should be. So the process to do that was to get it up and running, sync it to the grid, and then to command the blades to pitch into the wind immediately. And the drag that's created is audible. You can hear it, just a whining sound, and the blades slow down to almost a stop in a quarter of a revolution. Then you hit the emergency stop and it puts the brake on and stops it right now. So once it's stopped, the blades will pulsate a little bit, but you lose that blade pass frequency and that turning speed response, and you have basically a quiet, non-operating system that you just hit it with a hammer, and the hammer is the wind, or actually removing the wind. And now you have a nice sinusoid of the tower. And I mentioned before, a normal transient like this might last 2 minutes, and we only had about 8 seconds, and that's due to the limitation in the camera that we were using. There is another set of cameras that are coming out, and you have the option to get a 16-second ring buffer in it, or a 32-second ring buffer. I'm not exactly sure of that, but I think that's what they were explaining a little while back. Either one of those are fine. This turned out to be good. Those would be much, much better, and you get a nicer transient. We processed the tower video in the time domain to capture the event. We constructed a time waveform animation of the unit, and if we know the scale, in this case, we know that the nacelle is 9.8 feet across, we can get a good estimate of the motion. Okay, and we will get just simple cantilever beam motions in 2 directions, the drive axial direction and the lateral modes. Once we're done with that, we construct a Campbell diagram. We determine how much resonant margin we have, and if we're too close to a resonance driver, then we can do some correction at that point. But in this case, it turned out really well. Even for the bad ones were acceptable margin. All right, now we get to some animations. This is unit number 1. The animation to the right shows the tower natural frequency due to the e-stop and blade pitching changes that we talked about in a minute to stop the shaft. And you see mostly a dominant axial direction response and a little bit of lateral response. Okay, this kind of oval, eccentric oval is what we would call normal. And this was the leading turbine in the 190 turbine wind farm. This one's been running for 14 years and has never really had any maintenance on it. And it runs beautifully all the time. The actual measurements that we'll show you on the page on the next slide is we're going to calculate the natural frequencies. The expected frequencies are down here, 17.94 and 18.13. It's very close to 20% margin. That's kind of a design criteria that they shoot for. We exceeded that in both directions. We had something like 22% margin and 21.6% margin. This is the analysis, and don't get excited about doing math. This is the most simple math I think I've shown somebody how to do. You have a simple sinusoid. This is the tower motion. So I have the X direction motion in these first 2 plots and the Y direction in the bottom ones. So here is one cycle where I start at 0 maybe, or I start at the peak here. I go all the way to the negative and then back to where I started from. And if I know how long it took me to complete that circuit, that periodic event, I can calculate the natural frequency. So here's just running the numbers on that. frequency is 1 over the period. The period is right off the time waveform animation plot that you get, and the natural frequency was 18.31 cycles per minute. We can also see what the peak-to-peak displacement is. So from the lowest point to the highest point on here, I have roughly 0.682 feet, and that turns out to be about 8.2 inches. When you're looking up at the tower from the base, you can see the whole thing swaying, and it's pretty interesting to see. It's a big structure and it's moving, 8 inches, and it's visible to the naked eye. This just brings it out and gives you the actual values. In the Y direction, you have another periodic event. Remember, there's 2 natural frequencies for any cantilevered system. There's a stiff direction and a softer direction. This was a little stiffer, or a little softer, I guess. We find the period from the time waveform. Frequency is 1 over the period, and we calculate what the natural frequency is. That displacement was about 4 inches. So we had mostly an X direction or an axial direction vibration in that first mode. In the second mode, it's about half that amount of displacement. When we're done, we plot all this information in a Campbell diagram. If you're not familiar with this, it's basically a plot of frequency versus frequency. So the natural frequency are plotted as horizontal lines, and these are the 2 that we just calculated, the 18.31 and the 18.24. They're plotted as the horizontal lines here. Our frequency range, or our operating range, is 15 RPM. And we have a little bit of variation on that just in case we overspeed or underspeed. This is our margin from 15 RPM to whatever our natural frequency is. Now, to have a resonance condition, you have to have a natural frequency, which we have here. You have to have a driving frequency. This is the 1 times RPM, or the residual unbalance. This is 2 times RPM, which would be looseness or misalignment. This is 3 times RPM, which is a blade pass frequency. If you have a crossing of one of these drivers with a natural frequency in the operating speed range, you have a resonance or a coincidence. In this case, we don't have anything that crosses through here. Okay, here's our 1 times RPM. There's our natural frequency. They're way outside the operating speed range, and it turns out to be about 20% margin. This is unit number 2. So I'm going to walk through 6 units here, and pretty quickly. I just wanted to show you the different motions and the measured natural frequencies. So in this case, we have 23%, 23.9% margin in the axial direction, and in the horizontal direction, the frequency is lower. We only have 14.8% margin. We're shooting for 20. It's still acceptable. It's just on the low end. And actually, this was the worst performing unit on the site. So you're seeing it's more of a thrust axially. There's a little bit of offset horizontally. Okay, but it's how close we are to that driving frequency that's what should be a concern. This is a unit, and I didn't quite shut it down or turn the camera on right, and I got a little bit of blade flexing up here. So I caught it right at the end of its response. This is unusual because it's horizontal motion. The dominant motion is in the lateral direction, very little in the axial direction. We still had plenty of margin. It was just the response was different than what it should have been, a little backwards. This is the same thing. I caught right the end of the rotation of that blade, and when it gets up here and comes to a stop, it'll flex a little bit, and then it gathers itself. So we're have very little motion in this one. This one looked like a pretty good response. It's in the axial thrust direction, tower mode, and we have a little over 20% margin. Okay, I just had probably a little extra energy in the video from that blade. You know, it's watching what is not moving or it's trying to amplify that, but at the same time, it has something that has lots of motion. And that's the thing I'm trying to suppress, is that rotational motion. Unit number 5, it had more lateral response again. It's still orbital type thrusting in there, but there was some lateral motion that was a little higher than expected. They both had about 19% margin, so it's still on a bad unit, but we might see it down the road here. I have a few operating responses that are part of our failure modes. And this last one has 19% margin, so good margin, and it's thrusting in the right direction. This just had some other subtle motions that we can see in the operating data that we need to interpret. Okay, so those are my first 6 units. The first one was a good unit. Units 2, 3, 4, 5, 6 are bad units requiring lots of maintenance, and things have gone wrong. So we're going to look at the operating deflection shape videos with the unit running. First of all, though, I plot all the responses on the Campbell diagram, found that my minimum resonant margin was 14.8%, so right about here, and my maximum resonant margin was 22%. So from here to here is my range. So I plotted all 12 natural frequencies that we calculated, 6 or 2 for each unit, X and Y. And I mentioned before all the drivers. This is 1 times RPM. It's just a ratio. The slope is 1 to 1. Here's 2 to 1, 3 to 1, 4 to 1 when you're constructing the diagram. If you're interested in this, I have a spreadsheet that creates it for you, and it's very handy if you wanted to email me and use it. This is the time domain ODS analysis. So the time domain includes all the rotating frequencies simultaneously. So right now, what do I have? I have a rotating shaft. I have a blade pass frequency, and I have any tower motion associated with that. So as I'm going past the tower with my blade, I'm pulsing the tower, and the tower in return is buffeting the blade itself. So I'll get blade modes, I'll get all kinds of things going on. What I really wanted out of this was a signature. So this is the good rotor, the first unit that we looked at. And what's good about it is that I got a nice clean pulse in both directions. There's a little bit of kickback on it, but everything looks uniform. So I'm thinking, you know, if I have a good running unit, it's doing everything repetitively. There's no oddball features to it. And this looks about as close as you can get to a repeatable pattern over and over, okay? I don't see any distortions. I don't see any motion in the nacelle. So it's not exciting the tower. The alignment looks good. There's no flexing in here. Look around these pitching bearings on each of these locations in the nose cone, and I don't see any distortion in there. And we'll run into that in a second. So that one's considered normal. This is abnormal. This is a time waveform animation, different unit. In fact, this is the worst unit that they selected. It shows a series of complex pulses that are not considered normal. And note the pulses in the blade roots. So if I look here and watch this, there it is right there. Little pulse as it went by. As it goes past the tower, what I think's happening is I'm exciting the blade, and the blade is like a tail wagging, and it works its way down to the root, and it pulses where it attaches right there. So it wouldn't surprise me if there was some wear or maybe even a crack in that pitch bearing inside the nose cone there. But looking at this, I see repeatable patterns, but there's a lot of distortion. So instead of having just a clean pulse every time a blade passes the tower, I have all kinds of other stuff going on here. And this, I believe, is indicative of maybe cracks in the blades. So there's some nonlinear event going on, and this is like in between each pulse, something else is happening. And what I've seen on some of these is as I pulse by the tower, the whole blade doesn't tend to move until it's off of that position, then it starts to wobble a little bit like it did there. Okay, so I do see these little pulsations right at the end. I see some blade interaction, and I think I have a color contour one coming up that shows that a little bit better. Yeah, this is the one I was thinking of, but it does show it a little bit better. This is another unit, time waveform animation. Shows a series of pulses that are similar to the good unit. So this one was considered not too bad. I pulled this out because I wanted to show you how the blades flex. You can watch that blade as it goes by. It's pulled in as it reacts to the wind. So that's where you get that spring energy. You got a lot of wind force pushing axially on this structure, and when we tip those blades 90 degrees, it loses all thrust and we spring right back. So we're doing two things. We're the blade springing, and the whole tower will spring when you shut down like that. The color contour just shows you a couple of flexing in the blades. Hard to interpret exactly what it is. This right here is a little ghost shadow that was in there from one of the blades going by. So there was a green stripe coming right there. I think it's on the next blade. Yeah, there's something that goes through there. You will get on these color contour plots, you're changing this light contrast here. So this looks like motion as well. It's just a shadow of the blade going across the tower. One of the logistical issues I had was what time of day, where's the sun coming from? Where am I going to set up to see what I want to see without the sun interfering and throwing a lot of shadows? So it was a little more difficult to have the world spin in a certain way that I'd get a good picture, but there's a learning curve involved. This is that motion in the nacelle, or not the nacelle, but the nose cone joints there where the pitch blade bearings are. And you can see the non-color one, you'll see some distortion as they walk through here, as they go by the tower. And here you see it in color a little bit to highlight what's going on. So there's, all three of those joints are moving. So you do get a lot of motion from the blade pass frequency in the tower. Oh, did I see something else? Yeah, this was something else. You see this motion in the tower or the nacelle. It's just a little bouncing motion. That was caused by this, by having these every other blade pulsations in there. Something really strange was going on in the nacelle there, but it didn't look like real smooth motion, and it didn't show up a whole lot. It's drowned out mostly by the blade pass frequency, and this was basically at turning speed. I was seeing a little jerky motion in the tower, and I can see it there a little bit if you look at it long enough. This is a frequency domain ODS analysis. So in the software, you can look at the time waveforms and do movies of those. You can look at the frequency domain. The drawbacks, if you will, are on a spinning structure, it won't spin in the frequency domain. In the time waveform domain, it will rotate, and we'll see all of that exciting stuff going on. This, though, gives us an idea to see how that frequency is behaving. So this is blade pass frequency, and I believe there's probably some misalignment issue between the main drive shaft and the prop on the end. And it's a good view here that you can see it's kind of a pitching motion, and it looks like an alignment issue. But we'll have to wait and see what the wind farm says and how these units react to that vibration over time. This is another one that's showing blade flexure. So you can turn it in different directions. So the nice thing in the frequency domain, if you don't like this view, you can go back and forth between the time waveform and turn the blades, ratchet them around until you get an angle that you like. And this shows 1 times RPM response. So I have my cursor in the frequency domain on 15 RPM, and I'm seeing kind of a misalignment looking response, but the blades are really flexing. So they're going past that tower and they're getting a good kick every time. It's impossible to see it in real-time speed, but very, very interesting to see in low speed like this. This is the blade pass frequency. So here that it's all vibration in the blades, very little in the tower. Over here we have a kick in the axial direction at 1 times RPM and more motion in the blades as well. One of the comments was the harmonic multiples shown here. Well, I don't show them, but they're more uniform like the good unit, but the raised noise floor suggests a developing looseness problem. So the spectrum has a whole series of harmonics at blade pass frequency. This is a color contour of the nacelle on one of the units at 1 times RPM, and the other one's at 3 times RPM that's not colored in. But this shows putting your cursor on 15 RPM and the blades pretty stand still, but the nacelle is pitching. So a few things to look for. 3 times RPM. Oh, I was going to say this thing looks frozen, and it does in the nacelle, but right here you see out of phase behavior in those 2 connection points. So there is some pitch ring bearing issue, I think, in this this unit. All right. I had all kinds of animations, and I thought it was going to take me forever to put them all in, and I probably could have put a few more in, but this is a good estimation on how to do wind turbine towers and get some good information out of them. The logistics are the key to this. I spent a day, and I just wasted a day trying to figure out what was the good view and things like that. But you know, it's all practical. It comes well in the end. By the 3rd day, I was setting up and ready to go, and had 2 or 3 good images in no time. If I could do all the units in this wind farm, I could probably pick out the ones that were good and the ones that were bad, and it would be a really nice way to get a good baseline of the field and know which ones are bad behavior units from the start. But anyway, we proved that it wasn't the tower. The balance guy thought that it was a resonance in the tower, and we didn't see that on that unit, which was the worst one, and 5 others that he said we should take a look at. This is the price list for ODS videos. It's a product that if you already have part of the MEscope software, you get a discount. So if you're starting from scratch, it's the most expensive thing. You have to buy the camera, the ODS software, the video software, and it comes to just under $20,000. If you already own MEscope, just the basic ODS, there's a chunk of money off of it. It's like $4,600 come off of it, and you're down to $15,400. If you own VT420, which is Visual Modal Pro or Visual ODS Pro or better, then you don't have to pay for that. And now you're down to $12,400. If you already own everything and you have a camera, all you need is the ODS video software, and it's $6,000. So you're not paying $30,000, $40,000, $50,000 for animation software, and when you're done, you still have the traditional ODS software from MEscope. You can do modal analysis, you can do operating deflection shape. They have products that do acoustics and finite element analysis, and now operating videos. So take your pick. There's there's a lot of good incentive to buy into this. I believe there's a 2-week package, and if you type in ODS Videos 10, ODS Videos 10, you get a 10% promotional package, so 10% off, and a 2-week period to play with it. And if you are doing a 2-week period, you can also give me a call, and I'll send you some raw footage from what I've taken in the camera. If you don't have a camera, you don't have anything, you just want to play with the software a little bit, that's a great way to get used to it and see what's there and see what you like. So I'd be more than happy to send you some animations of mine and talk with you about them, because I'm constantly interpreting what I'm seeing. And it's it's a whole new ballgame for everyone to see something like this. And it's not very intuitive, but it's very rewarding when you figure out the puzzle. Also offered on-site or webinar. I have some training classes that I'm setting up. I currently already have ODS and modal analysis training. That's the one in the middle here. There's a lecture, and then there's MEscope workbook, which is the software built into little projects. So there's like 12 to 15 projects, start to finish, every command you need. You never fall behind. You learn it, and I show you how to do it, and then you spend some time doing it command by command and drilling that into your head. Later on, if you put it on the shelf for a while, you can come back to your workbook and start right back up. So basically, it's forcing you to learn the software in the shortest amount of time. We're putting together a class for ODS videos training, the camera setup, lighting, things like that, the software wizard. There's hotkeys. If you've seen some of these other webinars, the hotkeys are little things that they're implementing, they're trying out before they put it in the hard code, and they're always coming up with great ideas. And there's workbook guided examples. We come to you. So if you buy one of these cameras, you want training, it's a marginal fee. We come to your plant site, we'll take video on your machines, and we'll diagnose your machines. Okay, that's the best learning you can get, is on the job training. And in this case, it's all your machines. It's not canned images and things like that we know all about. It's a whole new learning experience, actually. And we also have different things. We have introduction to vibration analysis. If you're not into it yet, online training, things like that. And we do webinars as well. So if you want us to come to you, that's great. If you want us to do a webinar, that's fantastic as well. And that's all I have. You still there, Sean?
Sure am, yeah. Fantastic, thank you, I appreciate it. Let me go over the one question that we did get on there. And the question was, do you need to know the distance from the camera to the base of the nacelle? And the simplest answer is no, you don't. And so the way in MEscope with ODS videos, the way we calibrate the displacement or the magnitudes, the way they all work in there is based on the number of pixels in there. But if you have a known distance in the video, for instance, I don't know quite maybe what Dan used in there, but if you know the width of the nacelle, or you have a measurement value that is a known quantity in that video, as part of the ODS video wizard, when you import your MP4 and you get to processing it, it asks you to select a distance. So you have a grid of points on there, and you're going to select a distance between, or not even a grid of points. You're going to select basically, the edge of the two points of measurement that you have on there, and you're going to set that. There's a entry form, a number entry, so you can put that in there, and it has all the different values, whether it's meters, millimeters, centimeters, inches, feet, whatever you need to put in there, whatever that value is, you input there, and then that calibrates the entire video for the software use, which is going to give you accurate, obviously, displacement numbers or magnitude numbers, which is what you're looking for when you're doing this vibration analysis.
Yeah. So, well, one of the questions along lines with that, if I put in, I have this video, I know this distance is 9.8 feet, but it's not in the X direction, it's not in the Y direction. One of the things I was talking to one of the Vibrant guys about was tell it it's a triangle. So put a line in here straight across. I know that's a known dimension, and the X component of it could be calculated and the Y component could be calculated.
That's
So
exactly
that we
right.
could, so that we could frame, you know, then even if you're wrong, the software automatically will correct for X and Y direction. Now, if I go back out in the field and I want to take this data again, I'm going to line up the nacelle so that it, you know, there's one direction that's X and there's one direction that's Y, and it's very clear cut. And this was the last hard lesson I had to learn on my week on site, was I got to do a better way of lining these things up. Aesthetically pleasing, yes, but not the easiest to determine X and Y directions.
Yeah, that's true. Let's see, another common question that we get asked, and I just want to give the answer for. People ask, can you use other cameras? Yes, you can use other cameras, but there's a big but, a big asterisk on it. The software, the program that's used in there was designed to be used with the Chronos camera that we do recommend that we sell. You can import any MP4 from another camera or your phone or anything like that. You can do that, and you can process the videos, but we can't really stand behind, you know, the accuracy of the results, or you're going to maybe get some strange artifacts. You know, you need to know your frame rate, all that other kind of stuff that comes from it. We know, and it was designed to work, you know, with the Chronos camera. Other cameras can work. We've seen good results even from cell phone videos, but again, it's just one of those things where, yes, you can do it, but we can't really guarantee, you know, that it's going to work the way you're hoping for with another camera. Let's see, other common questions, Dan? You got anything off the top of your head?
No, I'm about spent.
Okay. We have a number of videos. There's other webinars that Dan's done before with us. Other videos, you know, from the webinars on video or ODS videos from MEscope. We have all kinds of user videos and tutorials for MEscope use in general on our website and through our YouTube page. So you can always go through that and check that out. You can reach out to Dan directly on this, or sales@vibetech.com. Again, Dan mentioned the code for the next month. If you attend this webinar, you can use that code. You can get 10% off of your MEscope ODS videos purchase, or just a general MEscope purchase or upgrade. Any further questions? No.
That promotional code, that was ODS videos 10, and that's 10% off if you're interested in saving a little more money.
There you go, ODS videos 10. All right, well, thank you all for your time. Have a fantastic weekend. Be safe out there, and we'll be talking to all you guys soon.